Have you ever stopped to think about where our electricity really comes from? Today, we're going to pull back the curtain on the unsung hero of our modern world. It's a machine that sits at the very heart of almost every power plant. From roaring waterfalls to silent nuclear reactors, it's the device that turns raw, chaotic force into the clean, orderly electricity that powers our lives. We're talking, of course, about the turbine.
So think about that for a second. What on earth could possibly connect the blistering heat of a nuclear reaction, the crushing force of a waterfall, and the gentle, persistent push of the wind? I mean, these forces couldn't be more different, right? And yet, they almost all rely on one single, elegant piece of engineering to make electricity. So here's our game plan. First, we're going to look at why the turbine is truly the heart of power generation. Then, we'll get into the nitty-gritty physics of how it turns simple motion into massive amounts of power, megawatts of it. After that, we have to face the big villain in any energy system, waste. And finally, we'll explore the incredibly clever ways engineers are fighting that waste to build a much, much better system. All right, let's dive right into our first section, the heart of power. Okay, so here's the big idea, the fundamental concept. It really doesn't matter if you're burning coal, splitting atoms, or harnessing the wind. All of these processes create some kind of moving fluid. The turbine is basically a universal translator. It takes the straight line force of that fluid and masterfully converts it into pure rotational energy. It is the absolutely critical bridge between the raw power of nature and our electrical grid. But how does just spinning something create electricity? I mean, it sounds almost too simple. To really get it, we need to look closer at the mechanics. And that brings us to section 2, from motion to megawatts. So let's get a clear definition here. At its core, a turbine is a rotary machine. That just means it spins. You have a moving fluid, could be steam, wind, or water, and it pushes against a series of very carefully designed blades. The one and only job of this whole setup is to turn the forward push of that fluid into a powerful spinning motion. Now, the turbine doesn't work alone. Its essential partner in crime is the generator. If the turbine's job is to spin, the generator's job is to perform what feels like a little bit of physics magic. It takes that physical spinning and turns it into electrical energy. And it does this using a fundamental principle of our universe called electromagnetic induction. Let's walk through this energy conversion, step by step. Okay, step 1. It all starts with that moving fluid, steam, water, whatever, pushing against the turbine blades. Step 2. That push gets the turbine and a connected shaft spinning really, really fast. Now that forward motion has become rotational energy. Step 3. Inside the generator, that spinning shaft is turning a huge magnet inside a giant coil of wire. And here it is, the final, most important step. The moving magnetic field gets all the electrons in that wire excited and forces them to move together in a single directed flow. And that flow of electrons, that is electricity. Now, listening to that 4-step process, it sounds pretty perfect, right? Almost seamless. But in the real world, it's anything but. You see, every single energy conversion, and I mean every single one, faces a huge enemy. And that brings us to section 3, wasted energy. This right here is one of the most fundamental, unbreakable rules of the universe. Energy never truly vanishes. It just changes its costume. For an engineer, this is the whole challenge. Wasted energy isn't destroyed. It's just the energy that decided to turn into something we can't use, like the random jiggle of heat or the sound of the machine, instead of becoming the useful electricity we actually want. To keep score in this battle, we use the concept of efficiency. It's really just a percentage. It tells us how much of the energy we put in at the start actually comes out in the form we want at the end. And you know, in a system as massive as the global power grid, even a tiny 1% improvement in efficiency is huge. It can mean powering millions more homes with the exact same amount of fuel. So you can really think of this as a constant conflict. In any power plant, the useful energy is the electricity we want, the stuff we send out to the grid. The wasted energy is literally everything else. Heat that escapes into the air, the noise the machines make, the vibrations you feel on the floor. The entire goal of power plant engineering is to shrink that wasted energy column and grow the useful one. So where are all these energy leaks? Well, the main culprits are things like friction, where the spinning shaft's energy just turns into useless heat. There's also thermal loss, where super hot steam radiates heat away into the building. Even the turbine blades themselves aren't perfect. Some of that steam or wind always slips past without doing any work. Each of these is like a little tax on the final output. And believe me, they add up fast. Okay, so that brings us to the really exciting part, our final section, engineering a better system and the ongoing battle against all that waste.
So how do engineers fight back against these losses? Well, they have this three-pronged strategy. They attack the problem mechanically by cutting down friction. They attack it aerodynamically by perfecting the blades. And they attack it digitally by creating way smarter control systems.
First up, let's talk about friction. Every single bit of rotational energy that gets turned into heat because of friction is energy that can never ever become electricity. So, by using advanced lubricants and incredibly precise bearings, we make sure that shaft spins as smoothly as possible, transferring the absolute maximum amount of its energy straight to the generator. Second, the blades. This is so cool. Using powerful computer modeling, engineers can design blades with these fantastically complex aerodynamic shapes. They basically act like a perfect net, catching the most energy possible from the wind or steam. And special protective coatings keep them from eroding, so they stay in that perfect shape for a long, long time, always operating at peak efficiency. And this is where modern computing has been a total game changer. Smart control systems use AI to act like a perfect, vigilant operator, monitoring the turbine every single millisecond. They make constant, tiny adjustments to flow rates and blade angles, making sure the whole system is always running at its absolute peak performance, squeezing every last possible watt of power out of the energy source.
Maybe the most brilliant example of this whole efficiency mindset is the combined cycle power plant. See, a traditional gas turbine just vents its incredibly hot exhaust as waste, but a combined cycle plant looks at that waste heat and sees it as a resource. It captures that exhaust, uses it to boil water, and powers a second steam turbine, generating a ton more electricity from the exact same initial fuel. It's an incredible demonstration of recycling energy itself.
At the end of the day, the entire field of power generation is just a relentless, constant quest for more efficiency. It's a battle fought on every front, from material science and aerodynamics to computer programming. And it's all for one single goal: to honor that law of conservation of energy by turning as much of our planet's resources as we possibly can into the useful electricity that our world depends on.
Which brings us to a final and pretty crucial question. As our world's appetite for power just keeps growing, improving efficiency isn't just an interesting engineering problem anymore, it's a global necessity. So where do you think the next big breakthrough is going to come from? Will it be revolutionary new materials, smarter AI, or maybe something none of us have even imagined yet? The quest for a better turbine is far from over.